So this picture here, you have the elements of this theory, and then what you do is, what you measure in this axis is the amount of money that you have, or how much gasoline you have in your tank. And then the assumption is that you're consuming at a steady rate. So I guess you're driving at a steady, in a highway at a constant speed. So you're using this much money because you're purchasing goods at a constant rate. And so your cash balances are decreasing, and eventually they hit zero, and then you replenish. And in that sense, this amount is your withdrawal. Here, if time is measuring days, you're making a withdrawal, about once a month. So in a year, you're making, say, 12 withdrawals. The amount of money that you have at the time of a withdrawal, it's exactly equal to zero. Okay, that's kind of like Van Montovin, and what you decide in Van Montovin is, do you go there every month, or you go there every 2 months, or every day? And you're trading, as we know, the opportunity cost will be something like an interest rate with a fixed cost of each withdrawal, which is a typical inventory setup. Okay, so what do I want to point from this theory? So several things. First is that the Van Montovin model has only one parameter, which is this cost, this cost of withdrawing, and it has two elasticities, both of them equal to 1/2. The elasticity of average amount of money, and even though it's not looked at often because it's not in data sets, but for the number of withdrawals also has elasticity 1/2 with respect to both the opportunity cost and the cost. Now the cost is typically not observed, so these things are typically done by running a regression, and then you have all the problems you typically have. Who knows what's going on? Why do you recover orthogonality between your measure of R, your measure of the opportunity cost, and the rest? But we're going to take a different approach. Just want to remind you sort of how Van Montovin look like. So, oops, sorry folks. Okay. So one thing that before getting more into Van Montovin, one thing I like to show you is some idea of what is in this data set. So these are different years where we have these measures, roughly every 2 years. And then you have the amount of currency. That currency is normalized by the expenditure per day. So a number like in the top of 15 would mean that this household says they have a cash that in average, if they will use it, will last for 2 weeks. Just to give you an idea. Then it's in euros per person, just if you have curiosity about what numbers do they have. And then there's a bunch of other statistics that I want to pay attention to contrast with Van Montovin. So the first one that I want to show you is n lower bar over m. Now, remember what is n lower bar. There's a question in this survey is, when you go to a bank branch or to an ATM, how much money do you have with you before you withdraw? And the answer of that, in average, they'll give you a number. They also tell you in average how much money they have, that's m, so this is the ratio. So a number like 0.4, it means that when they go to withdraw, they don't really have zero. They have something that is roughly 0.4 of their cash balance. So think about the same idea that if you're going to put gasoline in your car, the idea is these guys are not letting it go to zero. And think about why you don't do that with your car, and probably it's the same reasons why you don't do that the same with your cash balances, if you want to have some picture in mind. So this is kind of different from Van Montovin in that respect. The second is the withdrawal relative to n. So there is this identity, this is truly an accounting identity in Van Montovin. If you withdraw this much, this many times a year, okay, C is consumption per unit of time. W is average withdrawal size. N is the number of withdrawals. So this is how much you withdraw times the number of times you withdraw per period. This is your consumption in that period. So basically, this is an accounting identity. Now, Van Montovin has as a behavioral, by making m lower bar equal to 0, that implies that the average amount of, that implies that the withdrawal is about twice the amount of money that you have. So I don't know if you remember this picture with a tooth path. That meant that maybe it's easier if I. This is time. So if you withdraw this much, if you actually saw how much money you have, this day you have W, this day you have 0. It's coming down at a linear rate. So in average, you have half of W. Okay, so if you look at the data, people have, they are making withdrawal that are smaller than that. Now, we are breaking these, all this data in those that have ATM cards and those that do not have ATM cards. So notice that the statistics for those that do not have ATM cards look a bit more Baumol-Tobin type of, and the ones that do not have, that do have ATM cards, they look more different. Okay, so what is this? This is the number, this is another statistics of the same. So what I want you to get from here is they withdraw before they hit 0. The withdrawals are smaller than what Baumol-Tobin will predict. And the second here is a similar statistic.
Do you immediately get the the second if you have the first? Like if the M lower if the M lower bar is positive?
No. It may not be obvious, but the answer is no. I'll talk about that later on. I'll talk about the drugs model, model that we're using for some scenario that has shocks. So the answer is no, but let me just, if I have time, I'll talk about it. So it's really not an implication of that because you could, well, I mean, I will talk now. Suppose that every so often, so consumption in this model is continuous, right? So suppose that sometimes you have to buy a big item. Okay, no, let's just do something simpler. Depending on demographics and stuff, but if you have bought the house already, you know that the day you buy your house, eventually at some point you have to come up with a check by the value of your house. Now that's probably a lot of money to have there for 6 months in advance. So what you do is you get that check kind of like an hour before. I mean, you typically sell your house, get a loan or something, and you get a check. Now think about how much this check contributes to your average cash balances. What is the answer? 0, because you have it for like a day. Okay, so when you have very large purchases, you make a withdrawal that is very, very large, and then this money has an infinite velocity because you withdraw it, and then when it's very large, you better just withdraw it right before. Well, imagine that there are certain expenditures that have that nature. So that then, in that case, you could have actually this statistic to be above 2, if you want. Because you could make a withdrawal. For instance, suppose the only thing that you do in your life is you buy houses. So what you do is you have to come up with the cash the day you buy the house. But the average amount of cash you have is 0, but the average withdrawal is huge. Okay, so we'll explore a little bit of that because we have other data sets that give us the distribution of consumption per size of purchases based on diary data. But I probably won't. I don't have time. But
so basically, when people say that velocity changes a lot in the aggregate, then they're kind of like implicitly thinking about these large ticket items. It's like the
good question. I'll talk about that. I'll give you a little bit of an application of this for the aggregate that I think is sort of so. But let me postpone it.